First, let's cover some administrative stuff. So, this course, textbook, is called Database Systems, the Complete Book by Jeffrey Ullman. And this is a very, very popular textbook for this course. In fact, it is considered the textbook. For every course in computer science and engineering and other areas, there is usually the textbook, or at least a short list of 3 to 5 textbooks that are known worldwide that they are the best textbooks for this specific course. And this is the case for our textbook here. This is a very popular textbook in the database world. It is like the book adopted by many universities abroad. And the reason why it's very well written, and it covers actually database 1 and database 2 stuff. So what you learned in database 1, if you get the whole textbook, you will see it covered from chapters 1 to 15, I believe, or 1 to 13 in the textbook, and the rest is for the content of this course. So what I do, because this textbook is not accessible to you in the university, that's not always the case. I will give you access to my copy, so you could actually read from it. And that's in the case that some of the content is not clear to you. So I actually also use the lecture slides provided by this textbook, but I have changed it over the years. It's still following the same organization as the textbook, but the content has been modified. Some slides have been changed to make it more explainable in my point of view, and some material has been added that is not necessarily covered in the textbook. But in terms of the organization and the order of topics, I'm going to follow the textbook layout most of the time. We will also be using PostgreSQL or PostgreSQL. I've put for you here the website. This is a very popular database engine. It is actually the #1 open source database engine. You have studied in database 1 how to work with SQL Server, and I believe you did an assignment and or a project on Microsoft SQL Server. PostgreSQL is on par with SQL Server. In fact, it has way more interesting features, in my opinion, compared to SQL Server. And it is suitable for the purpose of this course because it's open source. I will refer to you in certain slides or certain lectures about features in PostgreSQL and about documentation in PostgreSQL that you need to read and become acquainted with. In fact, at one point I also refer to you to some source code of PostgreSQL. Okay, so download it and start experimenting with it. It comes with a user interface called pgadmin that you need also to download. And once you install it, you have a database engine up and running on your computer. What we cover in this course is the internal architecture of a database engine, the data structures used, the algorithms built specifically or constructed specifically to be used in the database engine, and some optimization techniques that you need to be aware of. I also cover, towards the end of the course, NoSQL databases, which is quite an interesting introduction to the database world. And we will talk more about it later on and compare it to the SQL databases like PostgreSQL or SQL Server or Oracle and so on. Now, in my opinion, this is a very important course for you to learn in this period in your computer science and engineering education, because database engines are the second most sophisticated piece of software that could be written after operating systems. So the most sophisticated piece of software that you'll ever come across is operating systems, an operating system like Windows or Mac OS and so on. And the second most sophisticated is a database engine. I mean a SQL database engine. By studying database engines, the way we're going to study them internally, from the inside, what actually happens inside the database engine from the instance you send a SQL statement until the instance you get the result set back, will upgrade your computer science knowledge and skill, and also thinking. You will develop an appreciation for complex pieces of software, how they work, what kind of optimization you will have to consider. So this is not just some additional bits and pieces of information that you need to add to your knowledge base to be a good computer scientist, but this is a course that hopefully will affect how you think about computer science and how you appreciate writing complex, or how you go about writing complex software. So again, what is the objectives of this course? We will learn a lot about the internals of database engines. In fact, after this course, you will be able to browse through the source code of any database engine, and you will be capable of adding features or modifying existing features in the source code of a database engine. Now, as I mentioned, database engines are extremely sophisticated pieces of software. And if you would like to get a sense of how big they are, how sophisticated they are, I could tell you that they are in the millions of lines of code. So they only compete with, as I mentioned, operating systems. So for example, Postgres, depending whether you consider the plugins or you exclude the plugins, we are talking about a little bit more than 5 million lines of code. That's 5 million lines of code. That's a lot of code, okay? So we will learn how it's built, we will learn how it's architected internally, and we will learn why it's built like this, and we will learn how to optimize it. And this is a very important goal of this course, that you are able to optimize the database that you have built to run on the top of a database engine. So I'm referring here to the database like the ones you have created in database 1, where you use the commands like create table and create views, and you write some SQL statements against those tables and views. What you learn in this course will enable you to build better database applications. So it will change your thinking, or at least it will enhance your thinking about how you structure tables, or how you should not structure tables, or how you write queries, or how you should not write queries. Because if you know the internals of an application, then you are in a better position to use it, compared to using it as a black box where you don't know what's going on inside. So we will study everything that happens in a database engine throughout this course, from the minute you send the query to the second you actually get the results set back. A lot of things are actually happening. You will be surprised, what you have been using SQL Server in database 1, and you just created some tables and you filled in the table with data, the tables with data, and then you fire some queries, and you should have realized or noticed that the execution is actually quite fast. You fire a query and you get the result in less than a second. But actually, in that short duration, the number of things happening in a database engine are actually quite amazing, as you will discover in this course. I also, as I mentioned, I will cover and discuss the 4 types of the NoSQL databases, which is a new direction or a new initiative that has been around for at least 10 years, this notion of building what's called NoSQL databases. We will discuss why they are important, when to use them, and what are the 4 types, and what to expect from each one of those types, what's the pros and cons of each one of those types, okay? Now, the majority of the course is actually focused on SQL databases, which is database engines like Oracle or SQL Server or Postgres or MySQL. The list is actually quite elaborate. And the reason why most of the course is actually focused on SQL databases is because SQL databases are very feature rich. You get a lot of things from a SQL database. That's why people go and buy a database engine like Oracle, and they pay thousands of dollars to use it for their institutional information storage and manipulation. Okay, it is not a coincidence that Oracle is one of the top 5 software companies in the world in terms of market value, in terms of the number of developers, and in terms of deployment. Okay? People don't pay Oracle thousands of dollars for nothing. They get a lot of features. And what you will be surprised to find actually is that NoSQL databases have a very reduced set of features. And we will discuss that in detail. When do you need what, or why NoSQL exists, and what's the future of NoSQL. And if we have time, we'll also touch on NewSQL, which is NEW, NewSQL databases, which is basically a mix of NoSQL and SQL concepts. So we will come to that and discuss it later on. So throughout the lecture slides, I insert what's called, lecture takeaways or course takeaways. They are numbered from 1 in the first lecture all the way to the last takeaway you will see in the last lecture of this course. And these are like learning outcomes you need to remember when you're studying these lectures. The lectures are quite information intense. There's lots of information that's communicated through the lectures. But every once in a while, I will just put you a slide that says, okay, what you need to learn from all of what I have discussed before is this. And it's important, for you, if you, take anything from this course, is to remember these lecture takeaways or course takeaways. They will stay with you, in your career, basically. And it's not about memorizing them, but it's about, trying to help you to learn the material presented here. By consolidating what has been discussed every few slides in one bullet, one line that basically summarizes the whole thing. So let's start the course. Suppose you do an exercise in identifying entities in a specific problem domain, and you define this or identify this customer entity, for which you create a relation with the following columns: first name, last name, address, city, country, and birth date. And the types are listed after each column. Now, you go on later on and you start writing queries like the 3 at the bottom. The first one is selecting customers who reside in a specific address. The second one is selecting customers whose first name is some value that you are after. And the third one is trying to retrieve customers who reside in a specific country. This is a typical table and typical queries. Something you should have, done an analogous activity in database 1. Now, if you just create this table, fill it in with data, and you write these queries to start retrieving matching rows from this table, and that's all what you do, I would describe this as an abuse of database engines. Because the 3 queries at the bottom here will all run in O of n time. In other words, this query, like select star from customer where address equal to something, the code that will actually execute it will go and open the table, will go and access the table files on disk, and load the table content, and go row by row, checking on the address field if it matches what you are trying to find, and if it's the case, it will add this row to the result set. And the same thing for the following 2 queries: select star from customer where first name equal to something, or select star from customer where country equal to something. So we could easily imagine the code that will actually run or will address each one of those queries. It's going to be simply a for loop that goes from 0 to n-1 rows, from the first row till the last row, checking on the value. So that's O of n performance. And I would call this a misuse of database engines, because database engines are not used, they're not made so that you have O of n access to the data. In fact, if it is the case, if that's acceptable for you, then you don't need to use a database engine. you can just go ahead and store the data anywhere you like in your program, save it to disk, and then when the program starts again, load it from disk, and just write a for loop that iterates on every row by row from beginning to end, and find the answer to your queries. So database engines are supposed to give you a better performance in general than O(n). Database engines are made to store huge size information or huge data sets. We don't use a database engine to store information about 100 customers. You don't need a database engine for that. But we would use a database engine when we have 50,000 customers, or 100,000 customers, or perhaps 1 million customers. And with those numbers, with such a size, you cannot tolerate O(n). You see, if your customers are just 100, yeah, go ahead. O(n) is still fine. The difference between O(n) and log(n) when the customer size or the customer table has 100 rows is very, very small. But the difference starts to magnify once the customer size is huge. The difference between a customer table of 100 rows and a customer table of 10 million rows, given an O(n) performance, the performance will differ significantly. Consequently, we use database engines when we are trying to store lots and lots of information. And with lots and lots of information, O(n) is simply not acceptable. So what's the solution to our problem? The solution is, and this is the first thing you're going to learn in this course, there is an additional feature in all SQL database engines called the index. And an index is a data structure. It's a special type of a data structure. And you have studied data structures in your third course here in the curriculum. It's a special type of a data structure that is made for secondary storage. It's made to be stored on disk, the data structure itself. But it's separate from the table. It's something else. It's not the table. Okay? We have these data structures that we call them indices that are built on the top of the table, which means are built using the table data. How do I can create one of those data structures? I use the statement create index. I will give the data structure name. In this case, I'm calling it, the first one, calling it index or IDX underscore customer underscore first name on customer, and between brackets the column I'm creating the data structure on. So there's a number of things here you're learning. First thing is there is something called an index in the database engine. So this exists in SQL Server, this exists in Postgres, this exists in Oracle, it exists in all decent database engines. In fact, a database engine without an indexing mechanism is not considered a database engine. It's not acceptable to have a database engine without some kind of an index data structure. So the first thing you're learning is that there is something called index. And you can actually create the index just like you've created the table using the create statement. So you say create index, and you give the index a name, and you specify on which column or columns you would like to have the index created on. The effect of creating index IDX customer first name is that what will happen inside the database engine when you type this statement, the database engine is going to go and read the table customer and retrieve all the values in the first name column and create an index and pass those values to this index. Okay? I'm also creating here a second index, which is on country, and that's why it says, on customer country. So now I have two separate indices, one created on first name and a second one created on country. Now, what's the impact of using an index? When you run a query and the database engine finds out that you've previously created an index that could be used to answer the query, because remember, the index is storing the information from the column it's supposed to be built on. So when the database engine finds that there is an index already created, it will use the index. It will not go and do a sequential kind of brute force scan of the customer table from first row to last row. it will use the index instead. And the index is made in a way to speed up the access to any given value it is storing inside it. So IDX customer country stores the content of the country column in the customer table, but it's storing them, those countries, they're being stored in an efficient way. So if you'd like to look up any country, you can find it fast. And once you find the specific country you're searching for in the index, there will be a pointer beside each one of those country names that takes you directly to the specific rows in the table that has this specific country. So let's say you're looking for country Egypt. So you'd like to get all the customers whose country is Egypt. So when you query the index, IDX customer underscore country, it will give you, I'm just simplifying things for you, so I'm gonna present it in a bit of an abstraction here, as if it's returning to you when you query the index a linked list of pointers, where the pointers are taking you to specific rows in the table. And those are the rows that have country equal to Egypt. Okay? Now the thing is, these are special data structures, and we will spend some time studying them, that enable you to answer a query on the data stored inside the index in a much faster way compared to a straightforward, what we call sequential access. So it's not going to be O of n. Usually it's either log n or O of 1, which is much better than O of n. Now going back to our three queries, we had three queries. We created two indices, one to speed up the second query on first name and another one to speed up the third query on country. The database engine will automatically recognize the existence or notice the existence of these indices we created, and it will use the index, consequently will give you either log n or O of 1 performance. Now for the first query on address, because we didn't create an index, it's going to still run on O of n. So what this tells you is something very important, that indices are there for you to use to enhance the performance of executing any query. And there is also something here that is implicit that we will talk about later on in detail, is that we have many variations of indices. It's not just one type. So some indices will give us O of 1 access, which is great, of course, and some other indices will give us log n. Okay? So we will study these indices later on, and we will find out when to use each one of the available indices inside the database engine. But if you don't use an index at all, you're not really making use of the database engine. Okay? As I already explained. So what's the syntax here to create an index? Well, we've already seen that in the previous slide. It says create index. You give the index any name you'd like, and then you say on, and you specify the table name, and you can put either a column or a list of columns based on the index you're trying to create. We could also drop an index, okay? And dropping an index, just like dropping a table, dropping an index means delete the index, just like dropping the table means delete the table, okay? Now, how do I drop it? I just say drop index and I specify the index name. That's why we're giving it a name in the first place when we create an index, okay? Now, I'm going to give you an inside information about Postgres. Postgres stores the indices that were created in a table called pg_index. So if you ever access a database schema in Postgres, and you're wondering what indices were created before, you can type the query at the bottom here, and it will tell you which indices were created and on which column and which table, and in which table, okay? So this idea will pop up a lot throughout this course, that the database engine, any database engine, whether it's SQL Server or Oracle or Postgres, when you create a new schema, it will create additional tables to store information about the tables you create, and about the views you create, and about the indices you create. So we give them the name. They are called the metadata tables. So they are tables that contains information about the data. It's not what you insert, okay? It's not this the tables you create. These are tables that are created automatically and used internally by the database engine to track what you do, okay? It has two purposes. The first one is security, so you can always figure out who did what, who created this table, who inserted this row, and so on. And it is also used for maintenance. And this is also something that you really need to understand by now, that in database one you learn about how you build a schema, how you create a table, how you insert the row, how you update a row, rows, and how you delete. But there's a whole job called in the industry, in the IT industry, called the database administrator. It's a job, okay? Now, the job of the database administrator is to make sure that the database engine is always running as fast as possible, and it is not facing any problems or delays either from the database engine or from the underlying hardware. So basically, a database administrator job is to do day-to-day maintenance of the running in production database engine. And one of the things actually they will do is to drop indices and create indices. So creating indices is probably understandable by now, but the question is, why would we drop indices? And the reason why we would drop indices is because if you notice what I described in the previous slide, what we're going to do is we're going to create the table and then later on create the index. And I said that the index contains the information or obtains the information that is stored in the column, is being built on, and use it internally, or takes a copy of it and have it internally inside the index. But that adds an overhead. It will slow things a little bit in the insert, update, and delete, because now we have the information stored in two places, in the index and in the table. If you insert a new row, you have to insert it in the table and you have to insert it in the index. If you delete a row or rows, you have to delete it from the table and also delete it from the index. If you update a row in the table, you have to also update it in the index, and you have to do it this way because this is the only way that will enable you to always be confident that you could use the index and get as an output the correct result. There has to be a one-to-one mapping between the index content and the table content. But that means we are going to slow things down, because if I insert in the table before, now I have to insert in the table and the index, so I'm taking more time. Now why do we are then creating indices? Because it will speed up significantly the search, select. So we will tolerate, you know, the slow operation now in terms of insert or delete or update, for the gain in speeding up the select. And that should tell you something if you keep thinking about it. Well, this will work great as long as we're doing way more selects compared to insert, deletes, and update. And actually, for most database applications, it is the case. Let's say you're building a database engine for an e-commerce website. You upload your products. Let's say you have 10,000 of them. Okay? Not 10,000. Let's say you have 100,000 products in your e-commerce website. Now, how many searches are you going to get per day? Now, if you just have an average of 1,000 users visiting your website in a single day, and every one of them will search for one product only, you are getting 1,000 searches per day. Okay? So, that's 30,000 per month. That's almost 360,000 per year. And if you are going to pay an upfront price, because when you insert the 100,000 products, you were inserting in the table and later on in the index, well, your gain is much more, because you're going to spend the whole year running those 360,000 queries much faster than if you didn't have an index, because all of those guys will run in either log n or O of 1 compared to O of n. Okay? So, but the point is, what I need to communicate to you is that the index involves a price. If you create too many indices, you will slow the system down in insert and update and deletes. So there has to be a careful balance between the number of indices you create and the amount of data you have and the number of tables and columns you have. Okay? So thinking naively about it, I say, okay, if the index is such a great idea, if I have a schema that has 20 tables and in total, say I have 100 columns, so on average every table has 5 columns. What about I just go ahead and create 100 indices? Well, that's really a bad idea, because you're going to maintain those indices. They're going to, of course, consume memory, and they will slow down inserts, updates, and deletes. Inserts and deletes might not be that important, but updates, if you think of an e-commerce website, are very frequent, because every time a customer buys one of your products, you decrement the stock by 1. So now you're going to do lots of updates if you're selling a lot on your e-commerce website, okay? Just as an example. So the idea here is that what I want to communicate to you is that, yeah, indices are great, but they involve some price we have to pay, which is that they slow the insert, update, and delete a little bit. And if you have created previously an index and it's not being used anymore, I mean by that the query that you were trying to speed up, and that's why you created this index initially, is not anymore a popular query, that none of your users are executing the function that will result in running this query, then what you need to do is to drop the index. Okay? Because there's no need for it. It's just an overhead now. Now, who will do this? Who will monitor the traffic to the database engine? Tracking through the logs of the database engine, what kind of queries, what kind of selects are being sent to the database administrator. They would keep a log, daily log and weekly log, and analyze the queries and figure out, oh, okay, now this query is not anymore popular. No one is really, sending this query to the database engine, and this query had these 1 or 2 or 3 indices created, and since no one is sending the query, no one is going to use these indices, so let's just drop them from memory and delete them from the database engine. Okay? So this is the role of a database administrator, at least one of those roles. Now, if you're newly appointed database administrator and you go to a company and you have no idea, what indices were created, if you're working on Postgres, you can just type select star from pg_index and you will see what indices exist. And this is really what metadata is all about. That this notion of storing information about the data itself. So here's your first takeaway in this course. That an index is a data structure built on one or more columns to enhance the performance of SQL queries on those columns. Without an index, the database engine would be doing linear search in the data to answer a query. Using an index, either you enhance the performance to log n or O of 1 based on the index type. Now let's look at the architecture of a database engine. Most SQL database engines in the world will follow the architecture presented in this slide. Okay? Why? Because it's a very nice division of subtasks involved in executing a query. I will just explain it from left to right, top to bottom, and pretty much that's what we spend all the course on, these components that shows in front of you. So you type a SQL statement. SQL is a 4th generation language. It's just like Prolog. You don't say how to execute things, you just say what you want. In Prolog, there is a unification process, or is a resolution process that happens that will take your clauses and figure out what to do. Now in SQL, it's another story. It's still fourth generation. If you look at, for example, the select statement, it says select stuff from where so and so, but you don't say how you do it. You just say I want this, okay? Now, this statement could be understood in a number of ways. And the query processor role is to translate it to something that is actually more concrete, that involves actual steps to be executed, okay? So this is what the query processor does. And the query processor is the module that will tell you, oh, okay, you have a syntax error in your SQL statement, okay? The query processor is doing a lot of very important stuff we will study, but there is a part of it that is not really in this course, which is the compilation part, or the parser and the scanner part, which is the module that takes your SQL and figure out that it is actually correct SQL, there is no syntax errors, and it will pass it to later on modules within the query processor, which we will study. But that just little part about validating the language that you're passing. Let's say, for example, instead of typing select star from, you forgot the star, and you just said select space from so and so, okay? And that was a violation of the SQL international standard, the ANSI SQL standard, okay? We have, by the way, a number of standards. Every few years there's a new update to the SQL language syntax that gets published. The very popular one you will find a lot of information about online is called SQL 92, but there were other versions of the SQL language that were also standardized, okay? Now, that part which is checking the syntax of what you've written, that this is a proper SQL statement, is done by a module called the parser and an accompanying module called the scanner. We don't study them in this course. You're going to study them in the compiler's course in the 9th and 10th semester. But the rest we will study. So the query processor will do some optimizations we'll talk about later on. Now, the transaction manager will take the output from the query processor and create a container that we're going to call it the transaction, which again we study later on, and we'll pass this transaction to the scheduler that will actually start to execute things. Buffer manager, log manager, and recovery manager are together working to ensure something very important that you get from a database engine. That's why people pay for proper, decent database engines. It will give you some guarantee about or protection of the data that you're storing. Okay, so we will introduce later on this notion of consistency of the data, and this is really what the buffer manager, recovery manager, and log manager gives you. Right? Database engines are unique in how they protect the data. I'll give you an example. Let's say you were coding on any integrated development environment like Eclipse or NetBeans or IntelliJ, and the current goes off. When you open the project you're working on, you might find that the last part you were coding is gone. It was not saved to disk. Actually, with Eclipse, the current doesn't have to go on to this happen. Sometimes just Eclipse crashes, especially Eclipse for Android. Okay, it just crashes, and the whole project is gone. Okay. With database engines, what we will study, we will figure out actually what we will learn is actually there are mechanisms in the software that ensures that this is not going to happen. The data is not going to be lost. You will always be working with some meaningful, we will call it consistent data, that ensures to you that whatever you're doing is valid. And again, we will come back to this topic and discuss it in detail. Now we will start the next part in the course with the component at the bottom, which is the data files, how the table is actually stored on disk. And this includes how the indices are stored on disk, because there is something again here that you should have noticed by now, that throughout your computer science education up till now, you really didn't develop any form of consistent data storage. So in your previous courses, you always worked with the data in memory, and when the program terminates, nothing is saved to disk. But with the database, or in the database world, this is not acceptable. First of all, the size of the data we're working with will not fit in memory, so we have to save it to disk. And the second thing is, we need to save the disk to make sure that in case of any trouble, let's say the current goes off, we can find the data when we come back live, when the server starts again. So we can load it from disk to memory. Okay? So we will talk a lot about this part, because this is where the data is stored. This is how the indices are created and how they are stored on disk and so on. Okay? And there is another type of data that gets stored in the database engine, which are the logs. And the logs are actually created by what's called the log manager. It's basically this guy is sitting in the shadow writing notes about everything that's going on. Nothing happens in the database engine without being logged, without being stored. Not the action itself, but the consequence of the action. Okay? So if you do an insert, the log manager will write, okay, I got this insert and it was written to disk. If you do a delete, the log manager would write down, oh, I got this delete and it was deleted from disk. Okay? So everything, any change that happens, whether it's insert, update, or delete, gets described somehow, as we will see, in the log, which is separate from the execution of the query. Okay? So there is, if you delete a row from a table, that is done in a transaction. But the log manager will also write down in a log file that on this time, basically I had this query and it affected this table and it deleted this row. Okay? And this happens all the time. So what we will start with today, what I like to introduce in the course is a little bit of history and building up to the current status of technology, because a lot of the things that appeared many years back still influence us in one way or another. Okay? So we will talk about two things: how files are organized on disk, and the first appearance of indices, which are called conventional indices, many years back. And I will also introduce in this lecture a modern index that exists on many database engines, that is based on the ideas of conventional indices. So let's start. So let's try to understand how we will store data on disk. And to do that, let's try to also understand first, what are we trying to achieve? You have a schema consisting of many tables. If we just try to simplify our solution here to the problem of how can we store things on disk, we can say every schema will be stored on a file. We will create a file on disk for every schema. Now, that will work. But there is a problem. The problem is, if you put a file on disk, and next you try to load it, the file needs to fit in memory. If it doesn't fit in memory, you will not be able to load it. I will give you an analogy here. If you've ever tried to open a video that's too big to fit in memory, if you've configured your operating system to have 0 virtual memory, which means you're not extending your physical memory, your RAM, with space on disk, because with virtual memory you get some space on the hard disk, and you tell the operating system, use this space as an extension of my physical memory, my RAM. And that's called virtual memory, because it's not really there. Okay? But if you've set your virtual memory size, and this is, by the way, defined inside any operating system, if you set it to 0, and let's say you have 4 GB of RAM, and you download this video that's 6 GB, when you try to load it, it will not load, because you cannot fit 6 GB in 4 GB. So following the same way of thinking, because remember, we use a database engine because we expect or we already have huge data size. Okay, we always think of, I'm having a huge data size. How can I work with it fast? So the assumption here in the database world that we will always have huge data size. You will have data in the gigabytes, or at least in the hundreds and hundreds of megabytes. So now you run into a problem. Let's say you have 20 tables, and every table is on average 250 megabyte, and you have 20 tables, and you only have 4 gigabyte of RAM. You cannot load the 20 tables in memory at the same time. In fact, you cannot even load half of them in memory at the same time. Because if you multiply 20 tables by 250 megabyte per table, okay, that will give you a lot of, you will need a lot of space. So 4 gigabyte is not enough. So a better solution than saying I'm going to store every table, every relation in one file, is to split that file into several files. And we will call them in the database world a block or a page. So instead of storing a table in one block or page, I will store it in n blocks or pages on disk. How do we do the division? We'll talk about later on, but I can give you up front, an idea. Let's say you have 100,000 rows in a table, and you decide to store this table using 5 pages or 5 files. So you would store every 20,000 in a page or in a file or in a block. It's the same thing. Means the same thing, okay? But then you need to keep track of things. You need to know that in this file or block or page, I'm storing from row number 1 to row number 20,000. And in the second one, I'm storing from row number 20,001 to row number 40,000. And in the third one, I'm storing from row number 40,001 to 60,000. And it goes like this, okay? So, if we're trying to imagine or think about how we store data so that it's in the table or in our schema so that it's permanently stored, when we switch off our application or when the current goes off and then the system starts again, we need to find the data, we need to store the data. The solution is going to be split every table in your schema to blocks and store the data in blocks on disk. Now, this will also give you an advantage, which is, as we said, you will be able to load the table into memory now. Because if the table size, say, is 6 gigabyte, and if you store it in one file, and you try to load it, because you have a select statement and you're trying to run a select, if your server has 4 gigabyte of RAM, you cannot fit 6 gigabyte into 4 gigabyte. But if you have split your table into, say, 10 blocks, so every block will have 600 megabyte only out of the 6 gigabyte, because you have 10 blocks and 6 gigabyte tables, so that's like on average every block will have 600 megabyte. You can definitely load a 600 megabyte file into a RAM that is 4 gigabyte. And in fact, you need that, and this is really the advantage here. Now you can run joins. Because if you're joining 2 tables, then you need to open the 2 tables to have access to the rows to find out the column whose value that appears on the first table and also appears in the second table, okay? Because this is how you do a join, okay? Now, so you need to open 2 tables. So if you're always splitting your tables to smaller blocks, okay, not one big file, but smaller files that we are calling blocks, you can load now 2 tables at the same time in memory to be able to do the join. And when you're done with these blocks, you can remove them from memory and bring another set of blocks and put them in memory to continue answering your join query. Okay? So this will enable us to actually execute SQL statements. So we moved from the idea of one table equal to one file, or one table stored in one file, to one table stored in several files, and we're going to call them blocks or pages. Why did we move that way? Because we are thinking of what are we trying to achieve. You know, if you think of high level, what do you do in the SQL? You insert, update, and delete. So I would like an easy way to do insert, delete, and deletion of tuples. I also do very frequently selects, so I would like a way to actually be able to go through the table and look for a value. Okay, whether matching a condition like SSN equal to 1, 2, 3, or just grabbing all the rows in the table. But that brings me to a more fundamental question: can I load the table into memory? And the answer is, if you put it in one file and it gets too big, you might not be able to load it. But if you always split it into smaller files, yes, you will always be able to load it, and consequently, you will always be able to execute any query you like. Now let's go into a bit of history. What shows up here are the first hard disks that were invented. In the far left, you have what's called a tape, a paper tape. I actually have one of those, and usually in the lecture, if we were doing this live, I would get you the tape, and you would be very entertained, you know, with how it looks. It's basically almost like your belt that's very long. It's made of paper, and the holes are actually used to represent ones, and the no hole represents 0. So obviously, you can only do one time here of writing, because once you make a hole, you cannot unhole it. Okay? You cannot fill in the hole with something. So this was what's called a write once hard disk. Okay? Now, the idea obviously was an innovation in itself, but people realized, or researchers realized, that we need something better. So what you see in the middle is the better, which is the magnetic tape. And you should have seen this if you have any old cassettes at home. It's exactly the same technology. Instead of using physical holes, we use magnets to magnetize and demagnetize an area. Where there is a magnet, it's a 1. Where there is no magnet, it's a 0. Okay? What you see on the far right is actually how you read it. You put it in a device. So the storage is decoupled from the reading and writing device. This thing that appears on the right, there are 3 of them. Each one of those could be considered as a hard disk by itself. Okay? This is obviously, if you want to get a sense of how big this is the size of the fridge, of your fridge at home. Each one of those. Okay? IBM made a lot of these guys, and they made millions just selling these very retarded devices. Now, a very important idea here that still exists with us, or at least traces of it still exist with us in the database world, is this notion of sequential file access. What sequential file access means is that you start from the beginning and go all the way till the end, passing through all the data, one row at a time, until you're done. So, if you'd like to think of an analogy to this from your early courses, the idea of a linked list. A linked list, you have this set of nodes connected together, and to do anything in the linked list, you have to start from the beginning, and you could go all the way till the end. There's no way to jump inside the linked list, at least not with the traditional linked list data structure. You can't jump. It's not like an array where you can jump to any cell. You have to go one by one from the beginning to end, to visit every node from the beginning till the end. That's the same idea. And actually, where the linked list is coming from, in terms as an idea, as an innovation, it's actually coming from sequential file access. because this was the first time this ever was invented. So it must have influenced everyone that was studying computer science then. And when they started thinking of data structures, obviously the influence of sequential file access is very clear in linked lists. Okay? So let's move on. Now, sequential file access came along with one simple idea that was trying to answer the question, how do we find the data on the tape? Now you have this tape that you can magnetize and demagnetize. But let's say I would like to retrieve row number 10 and row number 20. Where are they located on the tape? It's not an easy question. You have to come up with a mechanism to identify where is the beginning of row number 10 and where does it end, and where is the beginning of row number 20 and where does it end. So to answer that question, fixed length records were invented or were proposed. The idea of a fixed length record goes like this. That's for every table, you study the columns that you have in the table, and you find out the length of every column in terms of bytes. And then you do an exercise trying to determine the maximum length that you will ever need. For example, if you look at this table I have here in the right of the slide, the second column is for town names. What you are after is the maximum size that you will ever need in terms of bytes for this second column. So if you're building this for the states, you're going to go and find out what's the longest name we have for a town in the United States. And say that name is 40 letters. So you say, okay, I'm going to set that to be my size for the second column, 40 letters. Okay? And you do the same exercise for every column. You figure out what's the maximum number of bytes you will ever need. I'm assuming here that we're using ASCII code, so every letter will be represented by an ASCII code, which is a byte, and every number or every letter, alphanumeric value will also take a byte. So really the answer is going to be a number of bytes. Okay? So you know the maximum for the first column, the maximum for the second column, the maximum for the third column. You add them up, and that's the width of your row. Okay? Why are we doing it this way? Because we want a systematic, simple way to be able to jump to the beginning of any row. By the way, in this lecture slides and in the textbook, the historical name for tuple, because tuple appeared later on, was a record. So it was not called a tuple, it was called a record. And every one of the values like A-102 or Perry-Ridge or 400 was called a field. I believe when you study database 1, the new terminology is the row is described as the tuple, and what's inside the row are called records. So there's a bit of a naming problem here, or because of the change in the utilization of those words. But I think the idea is easily to communicate. When I talk about a row here, which historically used to be called a record, I mean the whole thing, the three of them, A-102, Perry-Ridge, and 400. Okay? Now I want to fix the size of every row. Why? Because when I fix the size of every row, and I say, okay, if you tell me, like, I want to jump to row number 500, that's easy. I need to skip 499 multiplied by the fixed size of a row. Okay, so if the size of the row is 10, and I would like to skip 499, I will multiply 499 by 10, that's 4,990, so I need to skip 4,990 bytes on the tape. And then I will find the row number 500. Okay? This is what this formula is telling me. N multiplied by I minus 1. Okay, N is the number of bytes per record, per row. Okay? Multiplied by the number of the row I would like to stop at. Okay? So I hope this is clear. If I'm storing a row in 100 bytes and I would like to go to row number 5, it's going to be 100 multiplied by 4. So I'm going to skip 400. And then I have my fifth row starting there. Okay? Now, what's the problem here? Obviously, there is a big problem, as you probably already figured out. This is a waste of space, because we are assuming the maximum for every column, but we're not going to get the maximum all the time. Okay? So we're wasting space. Now, why did anyone think of this? This sounds like a little bit retarded, because remember, in those days, the storage was using magnetic tapes. And magnetic tapes used to be accessed using what's called rotary motors that produce rotations. So it's much simpler to program a rotary motor if the motions produced or required are multiples of the same thing. And that's exactly what you get here. So you either rotated one time to skip, say, 10 centimeters on the tape, or you rotated one time to skip 9 centimeters on the tape every time you rotated. So with every rotation, you can fix the amount of space you're going to skip on the tape. And this is what this enables. It enables the construction of basically simple hard disks, okay, where the rotary motion required, the rotating movement that is required, is actually quite simple. Okay? But obviously it comes with a price. We're wasting space. Now there are also other problems that will stay with us for a while. And, we're talking by the way here about technologies that appeared in the 1950s, okay, and 1960s. And you will see why the bits and pieces will fall into place. Why are we just discussing this now? Okay? So here is one reason why we're discussing this. Let's say you have this type of architecture, okay? How do you go about inserting a row? Now, the straightforward solution is always add it at the end. So always rotate the tape till the last row, and then after it, you skip the last row, now you have some empty space. Now, what do you do when actually you start to delete rows in the middle? Which is very common, in the database world, we insert and we update and we delete. So what happens when you delete a row here? Well, you have a problem, of course. Okay? The problem is those empty spaces scattered throughout the tape are not going to be usable because you're always inserting at the bottom of the tape, at the end of the tape. So basically what you need to do is you shift all the rows up so you have the empty space at the bottom so that you could utilize it for insertion. And this process of clearing up or removing the empty space scattered throughout the tape or the storage media still exists with us up till today, by the way. Even on Windows and Mac OS, there are tools. In Windows, it's called the defrag. If you just go to the command prompt on Windows and type defrag, you will get this tool that enables you to do what I'm just describing here. Why? Because always it's the case when you have scattered empty space, or when you have empty space scattered throughout the hard disk or throughout the tape, it's less usable than if you have all the empty space together in one area somewhere on disk. Now obviously here that somewhere is always at the end of the tape, but in your hard disk it doesn't have to be always at the end of the hard disk. But as long as the empty space are all beside each other, it's one big empty space, it's actually much better for the operating system when it's coming to store big files. So here they run into the same issue, and historically what was developed is they used to have these special machines. You take the tape from the hard disk machine to the defragmentation machine. You put it there and it defrags, which means it goes and shifts up all the rows and keeps the empty space at the bottom. Now, because of the problem of the fixed length records, specifically wasting space, another way of storing the rows on the tape was proposed. It's called variable length records. in variable length records, and this is, by the way, what we have up till today. This is now the normal way of thinking about it, is that the row should occupy just the space it needs. So if you have a column whose maximum weight is 50, but it's only using 4, then you just take the 4. You just consume the 4. If you have a column whose maximum weight is 16 kilobyte, but the content inside is 127 kilobytes, 127 bytes, you just consume the 127 bytes. You just use that space, okay? Now, what that means, which is, I would say, the more natural way of thinking about it, that the row should only occupy the space it needs, not the maximum it will ever need, but only the space it needs. But then you run into immediately a problem. The problem is, where are the rows on the tape? Because since we are getting away or getting rid of the idea of fixed length records or fixed length rows, and so we will have variable length rows or variable length records. One row will be say 100 bytes, and then it will be followed by another row that's 27 bytes, followed by another row that is 600 bytes, followed by another row that is 320 bytes. It could be any number. So it is not easy to jump, say, to the 5th row. How would you know where is the 5th row or the nth row? Okay? How would you know that? You would not be able to know that. There is one way you could think about it, if you keep thinking about this, which is to insert between the rows a special marker that tells you, okay, this is the end of a row, so what comes after it is the new row. But what that means, you will have to keep looking for those markers back and forth every time you're doing any kind of processing. So a better idea, which is what variable length records suggested or proposed, is to store pointers at the beginning of the tape, and those pointers are basically the addresses where the row exists from or at. The beginning of the row. So if the first row consumes 500 bytes, the second row will start at 500, because the first one will consume from 0 to 499. And then the next one will start from 500, and if it is 50 bytes, it's going to be from 500 to 550. So you store those numbers, the beginning address of every row. That's what you see here in the image at the top of the slide. What we have at the beginning is an area that is called the header. And in the header, there are several things stored. First, how many entries we have, how many rows we have in this table. Second, the address, or the beginning address on the tape of every row. And that's what these pointers that are coming out from the header going to the inside of the tape are basically telling you. Okay? So notice the first pointer or address will take you all the way towards the end of the tape. And then the second pointer will take you to an area before that, or an address before that, and so on. Because what was proposed here is that to start storing, or to store the rows by beginning at the far end of the tape, putting the first row, and then before it we put the second row, and then before the second we put the third row. So what that means is the area is, or the number of rows are growing towards the beginning of the tape, which is what the red arrow here highlights. Okay? This idea is actually extremely important, believe it or not. In fact, if you have taken any media courses, you know that there are a number of media formats that follows the same way of thinking. So even though we don't have tapes anymore, the idea stayed with us. There are many media formats that would have in the file a header that tells you something about the content of the file. Okay, where is this coming from? It's coming from the database world, from variable health records, because this was the first time this was ever proposed. The nice thing about it is that we're not wasting space. Every row will just take the space it needs and nothing else. Okay. And the other nice thing about it here that maybe is not really visible to you the first time you see this is that we're storing addresses of rows. Okay, we are storing addresses of rows, and specifically the beginning address of every row. And this is a very influential idea that later on appears a lot in computer science and data structures. For example, if you remember your linked lists and binary search trees that you've studied, we used to store the addresses of nodes. Okay, the first time someone thought of that idea of storing the address of the node or storing the address of something to be able to access it, and instead of hard coding the places, which is the traditional way of thinking, I mean here is arrays, okay? Linked lists versus arrays, or trees versus arrays. In linked lists and trees, we're storing addresses of nodes. Where is that coming from? It's coming from here, from various health records. Okay? This is the first time this idea appears in the history of computer science, that we're going to store the address of something, and consequently, if we have the address, we can go to it, we have access to it. Okay? Now, this idea, when it was first proposed, it was about storing rows, but we can go higher level. We could think of each one of those blocks as pages or blocks, okay? And we store several rows inside one of them. And then we kind of replicate the idea again internally inside the block. Okay? But I'm not going to go there, but it's kind of alluded as well to this idea in your textbook as well. That's why, here, what you're storing inside each one of those that I have put a blue cross on could be a row, or could be a block where you have inside the rows. Okay? We'll just keep it as simple as just to think of it as rows. Next came an idea that still influences a lot how database engines are built. And the idea I'm referring to here is the sorting of the rows in a table. So instead of having the rows stored on the tape by the time of arrival, so you store the first row that arrives first and the second row that comes afterwards second, and so on, you try to maintain the data sorted according to some column of choice. So instead of the picture on the left, if we decide to sort by the last column, perhaps it's the customer bank balance, now we rearrange the rows so that the rows are sorted by the customer bank balance. So you see 350, 400, 500, 600, and so on. For you now, in the year 2020, this probably is like a trivial idea. Yeah, sure, what about sorting the data? But the point is, try to think of this being in 1950s or 1960s. At that time, scientists were still exploring how to work with a huge volume of data. Prior to the computer, everything was done on paper books or accounting books, and there is no notion of moving things around. You insert an entry according to the time of arrival, by date. Customer deposits an amount or opens a bank account today. He will be giving a serial number in today's ledger or today accounting books, and the value is inserted as of today. There was no sorting of entries in a ledger or in an accounting book or in a bank records.
But now we can sort things, we can change the order. So this became a very important idea because computer scientists realized that actually once you get the data sorted, you can do some really interesting stuff with it. Okay? In fact, if you go back to your CS3 data structures and algorithms course, we told you if the data is sorted, you can do binary search. And if you can do binary search, you can enhance the performance significantly. And instead of doing linear search in O of n, now you can do it in log n. Okay? So the idea of sorting also comes from the database world. But once you sort the data, you run into all kind of issues. Okay? For example, how do you insert now? Well, we have to insert the row in the right location to keep the data sorted. What if you insert in the middle and there's no space where you want to insert? Let's say you get an entry with the value 15 and you have 10 and 20. You would like to insert the 15 between 10 and 20. But 20 comes immediately after 10. There's no space. So you end up shifting down one row to be able to insert the 15. Okay? What if you have applied the scheme we discussed earlier, which is dividing the table on disk to pages or blocks, where you store part of a page or block, part of a table in each one of those blocks or files. So you got to find the right page or block to insert the 15. What if you go there and you find that the page is full of rows? You've reached the maximum capacity of the page. Now you got to figure out how to do it. You got to take the last row in that page and move it on to the next page to be able to insert your new row. Now what happens with deletion? If you delete in the middle of a set of rows, you will end up back with the defragmentation problem or the fragmentation issue that is solved through the defragmentation process. Okay? So this should give you a hint to something that will come up over and over in this course, and it's actually one of the main ideas that you need to understand. That when you have a set of related operations, in this case insert, delete, and search, if you speed up or if you design for one operation or if you speed up one operation by designing the data structure or the storage to support the fast version of this operation, like in this case, if we sort the data, we can do something like binary search. So instead of doing linear scan, we're going to get it in log n. So we're really designing for searching. If you speed up one of the operations, it almost guaranteed, but not necessarily always the same, but it's always, I would say it's most of the time, you will slow down the other operations. And that's what you see here. If we sort the data, search is fast, but insertion and deletion gets penalized. And there are other data structures that you might learn about in the future, where if you do the insertion fast, you most likely you are affecting the search or the deletion or both. Okay? So there is always this trade-off given any set of operations that work on the same data structure or in the same data. If you speed up one, the others are penalized. Now, another very big idea that comes from the 60s is creating an index. This notion that we're going to create another data structure, not the table, not the relation, not the pages of the table or the relation, but something else. And we search or we work with that something else, which is this data structure or index, instead of working with the table directly. Okay? The two main ideas up till now that really stands out, that will continue with us up till today, is that the table content is divided into pages, which is mapped to some kind of disk blocks. We'll talk more about that later on. But now we're dividing, from now on, we'll always think of dividing the table into pages. So while conceptually we would think of it as one big table, as one table, or which corresponds to one entity that you've identified in your system analysis and design exercise at the beginning when you were designing the database schema, internally this is cut into smaller pieces. That's one major idea. And the other major idea is that we are going to create something else beside the table. We're calling that the index, and we work through the index, or using the index, to do all kinds of operations on the table. Now, where is the index ideas coming from, by the way? Well, unfortunately, you haven't seen this, or perhaps it's fortunate, but I can tell you where an index is coming from. It's coming from a library index. So the question is, what's a library index? Well, you're not seeing that. That's why I'm saying unfortunate or fortunate, depending on how you look at it. Historically, libraries that had millions and millions of books was very difficult, actually, to locate any particular book when you're inside. Okay, let's say you go to the Library of Congress. In fact, I don't need to tell you about the Library of Congress. I could tell you about the library of my undergraduate studies. I did my undergraduate studies in the AUC, and the AUC then was the largest library in Egypt. It had about 300,000 books. The AUC library, then it was in downtown, was basically a building that occupied 4 floors. There were books spread out on 4 floors. So if you'd like to find any particular book, it's actually quite difficult. You will end up walking in aisles and aisles of books, endless books, 300,000 of them. So the way it worked is, in the first floor in the library, you will find a cabinet that had very small drawers, and the drawers are labeled with letters, A, B, C, D, and so on. And if you're looking for books about computer science, you would go for the drawer that has the letter C. When you pull that drawer, you will see cards. 1 card for every textbook in the library. Then you have to flip with your fingers through the cards to find out all the books, or skim through all the books they have that is labeled a computer science textbook, until you find the book you're looking for, or a candidate book. And then you will find its location. They will tell you on the card, it's the 2nd floor, aisle number 15. So you go to the 2nd floor, aisle number 15, and you start looking for the book. This is the idea of a library index. Okay? And that's what influenced database designers. They must have got exposed to that when they were studying in the university. Everyone was using, in the past, library indices. Okay? So the idea is you use something to go faster to what you're looking for. Okay? This is what an index is all about. Now, the first type of an index that was invented was called a primary index. The primary index is an index you build on the primary column. And the primary column is the column used to sort the rows. Okay? So again, I'm assuming here the relation is sorted on some column. For example, in the table that shows up on the bottom right, it is sorted on the 2nd column. That's why you see the branch names, or the suburb names, Brighton, Downtown, Minus, Perry Ridge, Redwood, and Round Hill, are sorted alphabetically. So that's like lexicographical sorting. The B, then the D, then the M, then the P, and so on. If you build an index on this column, then that index will be called primary, because it's built on the column that is used to sort the table. And of the primary, there were 2 types: primary dense and primary sparse. The primary dense is an index which holds 1 instance from every value that appears in the column. For example, if you look at the 2nd column again, it says Brighton, Downtown, Minus, Perry Ridge, 3 of them, Redwood, and then Round Hill. If you look at the index, which is what appears on the left of the image, where it says index in memory, there is Brighton, there is Downtown, there is Minus, there is Perry Ridge, there is Redwood, and there is Round Hill. So from every instance that appears, from every value that appears, 1 instance is included in the index. So even though we have 2 downtowns, we included only 1. we have 2 peri-ridges, we included only 1. Sorry, 3 peri-ridges, we included only 1. Okay? Now, the assumption is that this way you can answer any query faster by looking at the index and instead of looking at the relation. In fact, there is some type of queries that will save you loading the relation at all. For example, if you get select star from where branch equal to Heliopolis, you just need to look into the index to decide that there is no Heliopolis, and consequently you will never load the relation. Now let's imagine this is a big relation, as we discussed before, with hundreds of thousands of rows and tens of columns. So that's a lot of savings. And instead of loading something that is huge, now you load something that's quite small, which is the index. Because as you should have noticed by now, that the index actually is quite small. Because I'm going to include one value, or one instance from every value, and just a pointer to where that row is. So the arrow that comes out after Brighton is telling me where Brighton is, which row. Okay? And if we divide this into the table into pages, which page on disk and which row in that page. So that the total amount of space occupied by an index is quite small compared to the total amount of space typically occupied by a large table. Okay? Now, any query I get from now on, since I have this index, I will use the index. If I get select star from where branch name equals, or branch location equals the second column, I'm going to use the index. If I get insert, I'm going to use the index to figure out where to insert it in. If I got insert, into this, and the values passed, say Heliopolis, I know that the H has to come between the D and the M, the downtown and minus. So I know roughly where should I insert the Heliopolis branch. Okay? If I get a delete, delete from where equal to Redwood, I know where is Redwood. So I'm gonna, from the index, I will follow the arrow and I will go to this row that says A-222 Redwood 700. So I will be using the index all the time once I have an index. The second type of a primary index is called a primary sparse index. Again, this is an index built on the column used to sort the relation. But in this case, we're not going to have one instance from every value that appears in the index, included in the index. Instead, we're going to skip some in a systematic way and include one. In other words, we could do it like this. We could pick the first one and then skip 10 rows, and then pick number 11 and then or 12 and then skip another 10 rows, and then pick another row and then skip another 10 rows, and so on. So this is what you see here on the left side of this image. Brighton minus and Redwood were picked, and the rest were not included in the index. That's why it's called sparse. It doesn't have everything. Now, will we be able to answer queries and make benefit of this index? Yes, of course. But obviously, the benefit here is less. Let's say I get a query select star from where branch equal to Brighton. Well, I'm lucky Brighton is in the index, so I will track the arrow that points from the right of Brighton to the row that says A217, Brighton 750, and then I will scan in the table to find if the next row is also Brighton or not, and then I will stop because the next one is downtown, so I will include Brighton row in my result set. Okay? Now, let's say we got the query select star from where branch equal to Perry Ridge. Perry Ridge is not appearing in my index, but since I know this is a sparse index, it could exist in the table. It just was not picked to be included in the index. So I have to go to the table between the arrows that's coming out from minus and Redwood, which is the row A-215 minus 700, and all the way till the row A222 Redwood 700. And I will have to scan linearly those rows included within these two arrows to decide if peerage exists or not. And in this case, obviously, I will find peerage and I will include the three rows in my result set. So we are still winning. We are not necessarily, or not most of the time, not scanning the whole table. We are just now scanning parts of the table, doing linear search in parts of the table because of the nature of the sparse index, or because of the property of being sparse. So why would we use it? We would use it if the table is so huge in size. Remember, we're running always in the database world with the assumption that we will get stuck because of the size of the data we're working with. So we started by saying that if the table is so huge, we could be in a position where it doesn't fit in memory. So we ended up coming with a solution which is to divide it into smaller chunks or pages or blocks. So we split it up into pieces so we can load one piece into memory. What if you create a primary dense index, you cannot fit it into memory? The table is so huge that even a primary dense index now becomes so huge you cannot fit it into memory. Is that a likely situation? Well, not very likely in the case of modern servers, but if you think embedded systems, for example, if you think of smart watches or your microwave or your fridge at home, where you decide for some reason to include a database of items, maybe the amount of memory you're working with is so limited. It could be probably in the few hundred megabytes instead of being in the gigabytes. So maybe the space is so limited that you cannot even afford a primary dense index. So what's the solution then? Is to actually use a primary sparse index. And if you cannot fit the primary dense into memory, most likely you will fit the primary sparse, because primary sparse are going to be incredibly small. And they will still save you some time because you will be able to isolate the range in the table that you should be looking in instead of the whole table. So it's still beneficial, but not as much as primary dense in that respect. There is also a disadvantage here, which is that if you're trying to delete something, we've discussed this scenario when we discussed primary dense in the previous slide. If you'd like to delete something and it doesn't exist, you will not know it does not exist unless you go to the table and look for it. Like, for example, delete from where branch equal to Heliopolis. Well, Heliopolis could exist between Brighton and Minas, but you will not know unless you go there and check for it that it doesn't exist. Here is something you can also do. You could layer indices according to this way of thinking. Layer indices one behind the other. So what you see in this figure, the table first on the bottom right, and then there is a primary dense index that points to the table, and behind the primary dense index there is another index created that it is sparse. So when I'm executing any query, I would go from the outside one, the most outside one, the sparse, to a specific region or entry in the dense to the table. Now, why would I need to do that? Again, think here big. Say the table has 200 million rows. You create a dense index for it, and it has 75 million rows. You want to go processing the index faster. So you put on behind the dense index another sparse one. Now perhaps the sparse one will have like 5 million rows. What that enables you to do is to quickly isolate the range in the dense index that you should be considering. And consequently, you will quickly also reduce the number of rows you will be checking in the table. So these are called levels or leveled indices. Okay? You could put a dense behind it, a sparse behind it, even another sparse. Okay? And you can do as many as you like, but obviously you'll have to understand the impact on inserts and updates and deletes here, and it has to be valued against how much you're winning in the search. Okay? But we would do this again for the same reason I discussed before. Why would we use a sparse index? Which is that if the memory is not fitting your indices. So one way to handle the situation is to keep adding levels of sparse indices. And as you go away, one level away, or one level to the left, if you'd like, the entries in the sparse index has to decrease. So you make a gain. Like the example I was saying, you could have like a table that has, say, 600 million rows. You create a dense index and it has 120 million rows. And then you can create another sparse behind it that points to it, that has 50 million rows. And then you can create another one behind it that has 10 million rows. And then you can create another one behind that has 5 million rows. So you go from the 5 million rows sparse index to the 10 million sparse index, and consequently you're narrowing down a lot your searches quickly. Okay? This is almost like, if you like, and we will see this actually very soon in the next lecture, it's almost like building a tree, if you like. Okay? Where the root is at the far right and the leaves is at the far, sorry, the root is at the far left and the leaves are at the far right of the screen. Okay? We have a name for this. This is called second level because it's behind the first level. And this will be a second level sparse, obviously on a primary field, or on a primary dense, or it could be a second sparse on a second sparse, by the way. Okay? So both of them will work fine. So here are some takeaways. A primary index is an index built on the primary column, which is the column typically used to sort the table on the hard disk. Another takeaway: describing an index as being dense means that the index has at least one instance from every value appearing in the column we are building the index on. And I could add here that value is going to be, in the simple scenario, the first value that appears. And this is what you see in the previous lecture slides. So when we had peerage, I pointed at the first peerage. The fourth takeaway is that describing an index as being sparse means that the index has a small percentage, typically 10% of the values, appearing in the column we're building the index on. Now, you must be asking by now, okay, we have been doing these indices or creating these indices on the column used to sort the table. What if I'm interested in creating an index on a column that is not used to sort the table? Which makes sense. I'll tell you why it makes sense to ask this question. If you remember from your database 1, you were told that there is something called an auto-generated ID that most database engines support. And that is a unique number that identifies the tuple or the row. Now, we will talk about this if we have time towards the end of the semester, because this is a good idea as long as you keep using that ID in your queries. But sometimes you're forced to have queries that is not using this ID. For example, if the user is searching for a product, they will not search by the product ID. They would search by the product name, the product category. And these will be columns in your table. But the user does not know the ID, does not know if he's looking for like a Samsung LED 4HD TV, the ID is 11799. It doesn't make sense, okay? He will search by the title, Samsung, LED, 4K, Android TV, so on, okay? So, if you would like to speed such a query, then you create an index. But you're creating an index now on a column that is not used to sort the data. If you are creating such an index, we have a name for it. It's called a secondary index. So a secondary index is an index created on a column that is not used to sort the rows in the table. Is that possible? Yes, but it comes with a penalty. Because what we gained in the case of the primary index is not anymore existing now. What we gain in the case of the primary index is that it is created on the column used to sort the table. So the values are progressing. If they are strings, they are progressing according to lexicographical ordering. The A's, then the B's, then the C's, then the D's, then the E's, and so on. Okay? And if they are numbers, they are progressing by value, 10, 20, 30, 40, 50, 60, 70, 80, 90. But now if you go to a column that is not used to sort the data, the values in this column will be scrambled. you will see 10, then 5, then 3, then 20, then 23, then 7, then 9. Okay? Because this is not the column used to sort the data. So the assumption that there is a linear progression of values, which is used in the way the primary index, whether it's sparse or dense, works, that assumption doesn't hold anymore. So the penalty we pay here is that when we create a secondary index, we will have to create a first level that is dense and sorted from the values of the column that we're building the index on. And then we can put as many sparse indices behind that as we like. So this is the picture I'm referring to here. Okay? This is an example of creating a secondary index. I'm creating a secondary index on the third column that has, and if you look at the right side of the table, it has 750, 500, 600, 700, 400, and so on. But you see, because this column is not used to sort the table, the values are scrambled. They're not either increasing or decreasing, they're mixed up. Why? Because I'm sorting according to another column, which is the second one. That's why you see Brighton, the B, then the D, then the M, then the P for Perry Ridge, and so on. So the sorting is done according to the second column. It's not done according to the third column. So if I would like to create an index so that I could actually see the values organized, so that I could load it into memory perhaps and do binary search, I have to have the first layer dense. Okay? So the most crude version of this would be just grabbing all the values in the third column and sorting them. So you will see 350, then 400, then 500, then 600, then 3 700s, then 1 750, and then 1 900. If you get too upset with the abuse of space here, because we had 3 700s, you could do what is showing up here in this figure, where I make the 700 point to a linked list of references that tells me where are the rows that have the 700. So as you see, I have one where it says A-215 minus 700, and the second one where it says A-218 Perry Ridge 700, and the third one where it says A-222 Redwood 700. Okay, so this is what this picture is really trying to do. It's basically, it is building a secondary index on a column that is basically not used to sort the data. So we have, as you see here, the values dense. We have a dense first level in the secondary index. We could create behind it as many sparse as we like. Now, since we created this index, we get now a query. So I say, let's start from where customer bank account, let's assume this is the third column, is greater than or equal to 700. So you load the index into memory, the secondary index, which is what appears on the far left, and you'll use binary search to find the value 700. Once you locate 700, you scan all the way till the end. So you're going to add in your result set the 3 rows of 700, the 750, and the 900. So your result set will consist of 5 rows from the table. Okay? Again, these arrows that points to the table from this intermediate list are nothing but where is this row, which page on disk, and which row in this page. Okay? So it's going to be some addressing mechanism. Now, we could, as I mentioned, create a second level secondary index. Okay? A second level secondary index is a sparse one which must point to a dense secondary index of the same column. And I've already discussed that. So here is the fifth takeaway. A secondary index is an index built on the non-primary column. Here is another takeaway. A secondary index first level must be dense. We gotta get all the values sorted. The key about this, we're saying dense because we're interested in sorting them, to have them from the smallest to the largest. And then we can do binary search. Okay? Without that, we can't. Now we come to the very important discussion of this notion of page versus block. What's the story here? Okay? Now, you will be a little bit surprised of how things actually develops here. Now, here is the thing. To understand what is the optimal size of a page or a block, you have to understand how magnetic hard disks work, which is basically the hard disk you have in your laptop or in your computer at home. Okay? If you open it, I hope you don't, because you're going to damage it if you open it, but if you open it, the hard disk case, you will see that it consists of platters, or what you could think of as dishes. This is what you see up. You see in the left image here. Those platters, there are many of them. And there is a head that reads from the platter. What it reads is what's underneath the head exactly. And usually, not usually, but it is the case that the head, the reading head, is connected to what's called the arm or the boom. This is what appears on the right image. This thing moves, the boom moves to the inside and outside. And in the same time, the platters can be rotated through the spindle. So there are two movements here. Movement around the spindle axis, and the boom is moving into the inside and to the outside.
Now, why are we discussing this? You see, hard disks are an example of what's called electromechanical devices. They are devices that are made up of mechanical parts that are controlled electronically. And electromechanical devices where there is physical movement involved, and indeed we have here physical movement of the platters and of the boom, because of friction, because of electromechanical limitations, they are much, much slower than electronics. In fact, they are 1,000 times slower, at least. Now, that creates a problem for us, because if you would like to speed up the execution of any query, you would like to have a fast access to the data. But you can't have fast access to the data if your hard disk is 1,000 times slower your electronics or your computations. So, to decrease the impact of using such an electromechanical device, what we will try to do is to make sure that when we move the boom, consequently all the heads, to read from the hard disk platters, then we will need, and what we will read is meaningful to us. In other words, we're going to store the information that belongs to the same block, or let's call it with the proper name now, page, on the disk, in the cylinder, where a cylinder are the set of sectors that reside on the same perpendicular axis. That's what shows up here in this image on the far right, where it says cylinder. The cylinder is all the sectors that are underneath each other. For each one of those platters, there is usually a top surface and a bottom surface. That's why if you look at the boom, you will notice that there is a head at the top and there is another one at the bottom. Now, those sectors, or basically what defines a sector, is what the head can read. So if the head can read in one shot 16 kilobytes, then the top and the bottom of the platter will hold 32 kilobytes in two sectors, a sector at the bottom and a sector at the top in the same physical location, but one at the top and one at the bottom. So basically what we can read in one shot, and one shot means after moving the arm and stopping it at a specific location on the disk, are all the sectors underneath all the heads at the same time. Now, if we had stored our page or our file in separate, spread out locations throughout the hard disk, that means I will move the boom many times, or this arm many times, to just get the content of one file. But that will be an additional electromechanical movement or hard disk movement that we want to avoid. So instead, I will store the file content in the same cylinder, so that I can get all the content by moving the head or moving the boom and the spindle to stop at both at the right location, so that everything I read from all the heads I have and all the arms are meaningful. They make one file. Okay? Let me try to give you a little bit of a concrete example. So let's say I would like to store this image on the disk. Now, and let's say that the image is huge in size compared to the sector size. So say the sector size is 32 kilobytes and this image is 10 megabytes. So it will be cut to pieces and stored on separate sectors. This is how a file system will do it. So that's basically what we're going to do. We're going to cut it into pieces and put it on different sectors. But to try to minimize the boom movement, this is what we're going to do. Yes, I'm going to cut it into sectors, but I'll put it into smaller pieces, but I will put all the pieces on the sectors that are beneath each other, and that will be a cylinder. All the sectors underneath each other together make what we call a cylinder. So I will store all of these pieces of an image that I have cut it into one cylinder. And instead of just sectors spread throughout the hard disk, they all will fit on one cylinder, if I can, obviously, maybe I can't, but if I can, then I'm going to do that, okay? Why am I doing this? To decrease the need to move the boom again to another location to read the rest of the data, okay? Now, here's the thing. In the database world, everything is paged. The table is paged, which means it's divided into pages. The index is paged. The index itself is paged. All the levels of the index are also paged. Everything is paged. Even if you remember from database 1, materialized views, they are paged. Okay? Now, it's not just they are paged. The size of the page is actually the size of the cylinder, to make sure that we are moving the boom as little as we can. Only when we need to read a new page, we move the boom. Okay? So, historically in the database world, page sizes ranged from 16 kilobyte to a little bit more. And nowadays it's 64 kilobyte, and few hard disks are now standing at 128 kilobytes. Now if you're trying to put the pieces together, that's should be a little bit surprising, because this means if I have a table that is 400 megabytes, say, of data, millions of rows, okay, 400 megabytes. If you're asking me, okay, how many pages will it be stored in the 400 megabytes? Well, divide the 400 megabytes by 64 kilobytes, which is the page size, you'll get the number of pages that this table is stored in on the disk. Okay? Now, and this is the best thing we can do to avoid excessive mechanical movement. So here is the takeaway. Tables and indices are paged. Page size is related to the cylinder size. Now, let's go through an exercise of discussing what we have been discussing with paging now in mind, because paging is very, very dominant as a technique in the database world, and it causes all kinds of issues. Okay? So what you're looking at here, a relation on the right side, and then a dense index built on this relation. Okay? Now let's talk about this pointer before we move on. Just you're on the same page with me, because sometimes students are not really grasping the idea of this pointer. If I create my table is made up of text files, just plain text files, the pointer that you're seeing that has the title page, comma, row, the page is going to be just the file name on disk, and perhaps even the path to the file, which directory it exists in. And the row is going to be the row number, and that's basically it. Now, if you're not storing your table as text files, if you're storing them as binary content, you have to find the address of the row in the page in order to actually be able to extract the row. And the page itself will be just some binary file on disk. Okay? So I hope it's clear. Now, believe it or not, historically, the first implementations of databases were all comma-separated values files. Now, comma-separated value is basically having a row, a tuple, stored in a row in a file that is made of text, and the values are separated by commas. That's why it's called comma-separated values. So if I have 3 columns, the age, the name, and the phone number, so it's going to be like 20, comma, 20 is the age, comma, Ahmed, Mahmoud, the name, comma, phone number, 0, 1, 10, whatever. Okay, so that's the comma-separated values. So if you store your table as comma-separated values, it's going to be the file name, the file of this, the name of the CSV file, and the row number inside that CSV file will be the row that you're looking for. Now, again, we're going to page everything. The relation is paged, the index is paged. In the case of dense index, as long as I'm pointing to an instance of every value, maybe it's okay. But let me, because other scenarios, and then we'll come back to this idea. Here is how now a sparse index will look like. Again, the sparse index is paged. Okay? The table is paged and the index is paged. Now, by now you should be thinking, if you're trying to think of the code, you should be asking me, like, okay, I'm going to reach to the relation pages from the sparse index. But how do I know where is the sparse index? Pages, right? Like you have the page comma row information that takes you to a specific relation page or a specific page of a relation in the sparse index pages. But how did you know where on the hard disk are the sparse index pages? And for that, either you store it in a metadata table inside your schema, and this is why Postgres has its own metadata tables that I've talked to you about earlier. Or you can develop some kind of a scheme where you say, when I create a schema, I'm going to create a directory on the hard disk with the name of the schema, and there will be a directory inside that directory that has a file that contains the names of the pages of the sparse index. Or you could develop a third way if you develop a naming convention for those sparse index pages. So for example, if the sparse index name is index underscore employee, you have index underscore employee 1, index underscore employee 2, index underscore employee 3, and so on. Similarly, if we create a second level sparse index in front of a first level sparse index, it is as well will be paged. Now, why are we paging again? We are paging because we would like to minimize the hard disk movement. And we also have a secondary goal here, by the way, which is that we want to make sure that the page fits in memory. Obviously, it will fit if you're working on a server that has 4 gigabytes. But if you're working on an embedded system, again, like your smartwatch, the memory is quite limited. So you need to be able to fit the page to be able to use it. And if you page everything, then most likely you will be able to load it into memory. Now, let's talk about this trade-off of using sparse versus using dense. I've already kind of alluded to this before when I discussed with you that sparse takes less space, but we will be going to the table more. Dense takes more space, but we might in some cases even not go to the table at all and answer the query passed to us from just looking at the dense. Okay? This is what I mentioned here. In the case of the dense, you can tell if any record exists without accessing the relation file. Okay? In fact, there are many things we can do with the dense that will save us completely, prevent us or enable us to completely avoid going to the table. Like, for example, if you're running a SQL with aggregate functions, and you know that your primary dense index is not just built on a column that is the one used to store the data, that column is also unique. And since the rule for the dense index is to pick an instance from every value, and since the column is unique, if you would like to count the number of, say, where name is Ahmed, okay? Then if you find it, you'll find it once. Or if you like to count within the range, like say for example, all the first names that starts with A, you would like to find how many first names that starts either with A all the way till C. So all the A's and all the B's and all the C's. You know, all the first names that starts with an A and all the first names that start with a B, and all the first names that starts with a C, that starts with a C, okay? You can get all that from the dense index. You don't even need to go to the table, okay? Now we start to do some real simulations of what actually happens with real data. What's the issue here? Having a column unique is a rare case in the database world or in any schema you design. When you set a constraint saying that this column is unique, that is not the norm. The norm is that we will have repetitions. If you even think of names, if you even think of first names and last names, you will see repetitions, okay? How many individuals you have met that are called Ahmed Muhammad, okay? Or Ahmed Muhammad Mahmoud, or Muhammad Ahmed, or Mahmoud Muhammad Ahmed. Quite a lot, okay? So how many people have you met as well who live in Abbas La'ad, or whose age is 20? Quite a lot. So this notion of working with unique data, it actually enables us to do things much faster. But the problem is, most of the cases we have to live with and suffer actually from duplicates. Duplicates in the database world will always cause us trouble. Okay? So let's see some of the troubles here. If you're building a dense index and you decide to do, obviously this is a primary dense because you have the values sorted in the table, I mean on the right side. One way to implement it, that's if you're trying to avoid all troubles, but then you're going to waste space, is to include all the values. This is valid. Okay, this is valid because the rule for the primary dense index is that you should have at least one instance from every value. But you can include, I'm saying at least, but you can include all of them. That's what you see here. Okay? You're pointing to everything. But now you're wasting space because you have 10, 10, 10. Why not just 110? You have 20, 20. Why not just 120? And 30, 30. Why not just 130? Okay? You would think to do this optimization to decrease the size of the dense index. So you will do this. You will say, okay, I will point to the first occurrence of the value. So I got 10, 10, 10, I'll point to the first 10. I got 20, 20, point to the first 20. I got 30, 30, 30, point to the first 30. But notice now the problem. If you look at this, you have just introduced a horrible bug in the schema or in the database, because there is no way now you could reach to the page that has the 230s. It's just impossible. What's the problem here? The problem is you forgot about the duplicates. If you say I'm going to point to the first entry that appears of some value, the first time it appears, and you get lots of duplicates, and the duplicates span more than one page, you're going to miss all those pages that are full of duplicates because you're not pointing to them. Okay? So if you get a query select start from a value equal to 30, you're going to return one row in the result set. You should return 3. You must return 3. Okay? Why are we having this trouble? Because of duplicates. And we will see this popping throughout the course. That duplicates always, it's a trouble. We have to care about duplicates, we have to worry about duplicates, we have to come up with special rules for duplicates. So, to fix this, we're going to set a special rule that, yes, I'm going to point to the first entry that appears from every value, but I also want to make sure that I am pointing to a value in every page. So in this case, my primary density that I was trying to optimize will have a little bit more of values, will have some duplicate values, because if the duplicates are spanning pages, like in the case of the 30, I have to point to an entry there to get access to that page. And obviously my code that will do the insert and select and delete has to change, because if I'm inserting now another 30, I have to find where to insert it, and it has to be between the first 30 all the way you have space till before the 40. Anywhere between those in those pages is okay. Now, let's say we decide to just stick to the rule that we are going to point to an entry in every page. And we are not going to do the rule where it says I'm going to point to the first time I see a new value. That will be the scene we're looking at here. The relation on the right and the sparse index on the left. Now, I'm not showing you all the details of the sparse index, the other entries. And let's say the query we're working with is selecting the rows with value 20. Now, I'm showing this example to highlight that based on how you decide to pick values, your code will differ. Because here, if the rule you're enforcing is to pick to point to a row in every page, select star from or value equal to 20 will get you this 20 that you are referencing in the third page. But since you're only here enforcing that you need to point to every page, you're not enforcing that you will point to the first entry, the first time you see an entry. If you don't go back to the previous page, which is the page that is pointed to using the second 10 in the index, or the second page of the table on the right, if you don't go to that to grab the first 20, you're going to miss it. So the correct result set should be two 20s, or two rows. Every one of them has a 20. Each one of them has a 20. Now you're going to return a result set of one row that has a 20. Okay? So, the same thing for the 30. If the query selects star from or value equal to 30, you are pointing to a page that has two 30s, but you need to check the page before it, and perhaps even the page after it, to make sure that there is no more 30s. The page before it, in case there is a preceding 30, and there is actually one after the 20 in the third page in the table, and you need to check the page that has a 40, because there could be a 30 there as well. Okay? So, as you see, duplicates start to cause us trouble, because we don't know where they start and where they stop. And you have to always check before and after your found result to make sure that you're not missing anything that you need to include in the result set. So let's study how the deletion is going to work if we're having a sparse index. Recall, a sparse index means we're not going to have all the entries in the index. We're going to only have a subset of the index. And I'm showing you here actually more than what you would typically have. What you would typically have, as I mentioned earlier, about 10% of the entries only in a sparse index. But just to illustrate my example here, I'm going to use a sparse index that only is skipping a few values. So it's skipping 20 and 40 and 60 from the page. So it's basically picking one value and leaving the other. Let's say we would like to delete. What is the impact of deletion? Let's say we would like to delete the record 40. Well, first we have to find it. So we're not going to load the table. We have an index. We're going to make use of the index. Somehow we will access the first page of the index. As I mentioned before, there is a number of ways we can identify where are the pages that belongs to this index. So we will load the first page into memory, the one that has 10, 30, 50, and 70. We'll do binary search in memory. and we will find that we have these entries, and if 40 exists, it's going to be between 30 and 50. So we follow those two pointers, the one that's coming out from 30 and the one that's coming out from 50, hoping to find a 40. We will start with the 30, we scan down in the 30 page and we will see the 40, and then since there could be duplicates, we will have to go to the 50 page as well, and since there's no 40 there, we will stop. So deleting here 40 is actually not costing us a lot. We will just load one page that belongs to the index and two pages that belongs to the table. 40 exists in the first page that we're going to load. We will delete it, but nothing else will change in the index because the 40 was not in the index in the first place. So we're happy. 40 will be gone and everything stays the same. We loaded 3 pages, 1 index page and 2 table pages. We modified only one of the 2 pages that belongs to the table, which is the one that had the 30 and the 40, and we write it back to disk. Again, remember, since everything is paged, everything on disk. So later on, we'll actually perform detailed analysis of this loading of pages from disk. But for now, I'm just introducing the idea. If I ask you how many pages did we load here, it's only 3. How many pages did we modify or write back to disk? It's only 1. What about deleting 30? Let's say we would like to delete 30. Again, we are going to load the first page of the index. We will find the 30 right away doing binary search. And we will follow the pointer beside 30 to the second page in the table. We will load that, we'll find the 30, and we will remove it. But once we remove it and it's gone, now we will have to update our index because we have to have at least one reference pointing to every page. And since there will only be 40 in that page, we will have to update our index with 40. So consequently here, we will load 2 pages, one for the index and one for the table, and we will modify both of them, writing them both to disk afterwards. So we did 2 page reads and 2 page writes here. What about deleting 30 and 40? We'll follow the same logic, but now when the 30 and 40 are gone, the reference to that page is also gone. And consequently, we could shift, or we need to shift the values up. So we'll move the 50 upward. And perhaps we could fill in this new entry that exists at the end of the first page in the index with some value that will come in the future. Okay? So here we will delete the page that belongs to the table, and we will update our index, which means after loading it from disk to memory, modifying it, we'll have to put it back on disk. So we are doing here 2 page reads or 2 page loads, a delete, and writing back the index page. So 1 delete and 1 writing back. Now let's move on to see an example of deletion from dense indices. So remember, in the dense index, all the values appear in the index, or at least one instance from every value. So now, by now, you should be getting a little bit worried, because what's going to happen now, every time we delete something, we have to change the index page. We have to write it back to disk. So here is something that's actually good about sparse indices. Sometimes we did that, sometimes we didn't, because if the value doesn't appear in the sparse index page, we're not gonna be worried about writing it back to disk, because we load it from disk, it's still on disk, there is still a copy on disk. We load it into memory to be able to search in it using binary search. But when we are done and we didn't change it, we don't have to write it back. It's still there on disk anyway. But now with dense indices, this scenario will not work. Every time we do a deletion, we'll have to update the index. So here's an example. If I delete 30, I will find the 30. I removed it from the table's page, and I need to change it also in the index by removing it from the index, which means propagating 40 upward and erasing the 30, which means now I have to write that page back to disk. Okay. Now let's do insertion in sparse indices. We will find again that we are quite happy with sparse indices after this discussion, because again, insertion sometimes will be done without changing the index. For example, if you look at this example, if I would like to insert 34, so again I need to find where 34 will go. I will load that page, that the only page that exists in the index, into memory, and then do binary search to find where should I, where should I insert 34. It's got to go between the 30 and the 40, so I track the reference coming out from the 30 to the second page in the table, which has this 30 only and an empty row, and I put the 34 in the empty row. Okay, so this is nice. We have free space. We don't need to actually change anything. And then we write back this tables page, the second one, where we inserted the 34, we write it back to disk. What about 15? If we insert 15, well, now you start to see trouble. The reason why I'm saying that things are going to get complicated, because after loading the index page and figuring out where the 15 should go, which is between the 10 and 30, you're going to follow the reference beside the 10 to the first page in the table, and you will identify that, okay, I need to insert the 15 there. But the problem is, according to my example here, at most I could put 2 rows in a page. So I cannot put the 15 unless I shift the 20 down. Now when I shift the 20 down, I have to make sure that the index is properly set up. And that's what you see here. I shifted the 20 down, bringing the 30 even further down, and then I inserted the 20 as the first row in the second page, and that emptied a space for me in the first page, and I inserted the 15. But what I'm going to do as a result of that is I'm going to change my sparse index entry from 30 to 20, because if I'm keeping the rule that I will point to the first new value in the table, in the page, then 20 is the first new value now I'm working with. I haven't seen 20 before, and consequently, you have to update the index this way. Okay? Now you might have still kept the 30 as is, and you still point to it, because as long as you point to some row in this page, we are okay with it. It just depends on your policy, how you're actually building the sparse index. And in case you actually try to respect a certain policy that says you're going to point to the first new value that appears in the page, then you'll have to change the index page from 30 to 20, and consequently you'll have to also save that page later on to disk. Now, there is one idea here I'm going to introduce that will show up over and over in this course, which is that this business of shifting is quite troubling if you think of it carefully. And if all those pages we were looking at were full below the page that has 10 and 20, we could end up, in the worst case, shifting all the rows one location down, or one row down. And that could have like a ripple effect that goes from the first page to the last page in the table. Consequently, one strategy that many database engines would do to avoid this kind of rippling effect of shifting downward, is to create temporarily overflow pages. To put the 15 there and link it with the first page. So I would create a page, imagine we create a page to the right of the first page, and we link the first page to it, and that would be called an overflow page, where we put the new entries that are supposed to go to this page. We put it there in the overflow page, and we're doing this to avoid shifting everything down with a single insertion. Because imagine you get a lot of insertions, and many of them will cause things to shift down significantly. So you end up doing basically an O of n operation with every insert, or every couple of inserts, or every number of inserts. So instead of that, we could use an overflow page. Now, will the overflow page stay there forever? Not really. Database engines who would employ this technique would monitor the traffic, the number of SQL statements coming to the database engine per minute or per hour, and when the traffic goes down, when there is little traffic going to the database engine, perhaps people, this is a database engine behind an e-commerce website, and during the night most people will sleep. unless they are a computer scientist, of course, but you know, most of the time people would sleep at night. Okay, so when people are sleeping, the traffic is low, database engine realizes that, and when it figures out that it will figure out that this is a good time to actually go and merge the overflow pages into the actual table. Okay, this is just one way to avoid this, you know, ripple effect of shifting down things. Okay, this is an example of what I was trying to say. You try to insert 25 after finding its proper location. Well, if I'm actually going to insert 25, I gotta shift things down. Okay, instead of doing any shift, what I'm going to do is once I find this location, I'll just put it in an overflow page. This overflow block or page are not going to be permanently there. When the traffic goes down, this will be merged back, which means most likely it's going to be put just above the 30. If you know, at that time, the situation was still that was still possible. Okay. Now I'm not going to cover insertion in a dense index. We will run into all the cases we just described, except it's more expensive because we're more likely to shift things down. Because we have now the dense index with all the entries and also the column with all the entries. So if you're going to shift down in one of them, you're going to shift down in the other. You shift down in the table, then also you shift down in the dense index. Okay, so we run into the same kind of problems. So and generally it is more expensive because of shifting down in the index. Now let's discuss secondary indices and how they could treat duplicate values. Now remember, a secondary index is an index built on a column that is not used to sort the table, just like the table we have in front of us here on the right side. If I build an index on this first column, which is obviously not used to sort the table because the values there are not sorted, we said that the first level has to be dense. Then we run into an issue now when you have duplicate values. Because when you have duplicate values and you're just going to blindly copy all of the entries in this column and create a dense index out of it, you'll have lots of duplicates. This is what I'm referring to. I grabbed all the values and I sorted them, and I got these 3 10s and then 2 20s and then 4 40s and so on. Okay? And we previously said that in real life, duplicates are very common in many situations, in many data types, in many entities that you identify, there will be duplicates. Okay, that's why we ended up generating this notion of a unique key in the database way of thinking, just to be able to distinguish between entries. Okay, now you run into trouble when you look at this. You're wasting a lot of space. Why am I having 3 10s? Isn't it enough to just keep the references and say just 1 10? So here is the 10 and references, a list of references. We've seen this before. A list of references, where the 10 exists, and then 20, and a list of references where the 20 exists, and then 30, and a list of references where the 30 exists, and it goes like this. Okay? So the problem here is that we're wasting space, and we're wasting search time. Because if I'm looking for 20, I have to skip all those 10s before reaching the 20. If I'm looking for a 40, I have to skip all those 10s and 20s and duplicates just to go to the 40. Okay? So here is one option that I was describing. You put the value and beside it a list of references to where this value appear in the pages. But hey, remember, we also said that everything is paged, including the index. It's including the index. So now we run into an issue. I hope you can identify it. Can you identify it? Just look at the index now. Everything is paged. So the index also consists of pages now on disk. What we need to make sure of, and actually we will not be able to make sure of, the problem here is that we need our value and set of references to be contained within one page. Otherwise we'll end up loading more pages just to make sure that, or at least always one more page to make sure that there are no continuation of references later on. Okay? This is the same problem we've seen before. What we're looking at here is that there is no guarantee that my page size will fit me perfectly, in the sense that if you look at the first page of an index here, it has the 10 and then 3 references to 3 rows where the 10 appears, and then 20 and 2 references to where 20 appears. Let's say that the page size only enabled me to store the 10 and the 3 references to where the 10 appears, and then the 20 and then 1 reference to where the 20 appears. And the second one is not possible to store it in that page. So what we end up doing is going to the next page and adding a 20 there with the second reference to another 20. Okay? What that means, because everything is paged now, if we use this strategy, and let's say our query was select star from or value equal to 20, it is not enough to actually load the first page. When we see the 20, we have to load the second page as well to make sure there is no more 20s there. Okay? Because if we cannot put it in there, we will put it in the next page. Okay? Now, here's another alternative that's described in your textbook that people tried at one time, researchers tried at one time, and then they just stop doing it because it's a maintenance nightmare. And instead of keeping the value in the list of references to where the value appears, to the rows where that has this value, like the 10 for example here, what we do is we will link by adding a pointer at the end of the table that is not really visible to the programmer of the table or of the schema, it's only visible to the database. We will add a reference to where is the next 10, and that's what you see here. And then from there is a reference to the third 10. And in the third 10, there is a null, where it says there is no reference. It looks like a null value, okay? Because there is no more 10s. So we will link them through an additional column that exists, and we fill in with the next value, which is basically the next row to go to, okay? Obviously, we have a big problem here, which is that this is very difficult to maintain, okay? And especially if we're going to shift things up, all of these references will be invalidated, so we'll have to go and fix them, okay? So, or if we delete an entry in the middle, like for example, we have 3 10s here, one at the top, one at the bottom, and one in the middle. Let's say we delete this one at the middle, using some other column. Now we have to fix the references. We have to figure out what is the first 10 and link it to the second 10, which is going to be at the bottom, which is in the second page from the bottom. So now we go to another maintenance nightmare. Okay, so as I mentioned here, this needs an additional field that's going to be added. You need to follow the chain, but it's a maintenance nightmare. So people stop doing this. So here is the 8th takeaway. Sparse indices are generally more efficient than dense indices. Holding only 10% of the values, the index gets updated less often compared to the dense index. Then that's why a sparse is often considered more efficient in terms of the insert and delete and the update. So what we have covered up till now is, we've introduced conventional indices, we've discussed sparse and dense indices, we've discussed the notion of multi-level, we've discussed the problems that arises from you having duplicate keys, and I have discussed with you as well and showed you kind of steps how you would support deletion and insertion in these indices. We also discussed this notion of secondary indices that we could build as well, and we could have multi-level secondary indices as well. Now, the nice thing about conventional indices, these are historically the first type that appeared, is that they're simple to understand. I mean, they're very common sense. In fact, you could write it, or you could do this kind of manipulation or this kind of an index in any Java program or Python program you write. I mean, it does not require any more knowledge than what I just described, and most of it is just common sense ideas how you organize the data. Okay. Now, another thing about it that will become clearer as we see the other types of indices is that the index itself is actually quite simple. It's not that just how things are organized is simple. The index itself is just trivial. Okay, it's the value and a reference, Okay, we will see things later on that are way more complicated than that. Okay. Now, because also it is so simple, we could, once we load it into memory, we can do binary search and find out the result that we're after. Because it's just a simple array in memory, or if you like, just think of it that way. What's the problem here? The biggest problem is that Inserts and deletes are expensive. The deletes create holes. The holes require defragmentation. The inserts require shifting things down, and consequently, it's also a problem. What we will look at next is a modern index that appeared in the last 10 years that is built on the idea of conventional indices. It's kind of the child of conventional indices, if you like, or the grandchild of conventional indices. Okay, so conventional indices as a concept is very important to understand because they are the building blocks of everything that we're going to see later on. There's a lot of what we discussed today we will refer to and repeat in different contexts later on. But no modern database engine would support a sparse index or a primary dense index because it's too trivial. And plus, they come with the problems, as I mentioned. The problem of shifting and the problem of fragmentation, they're not easy to solve. And when you talk about tables that have hundreds of millions of rows, that becomes really a big problem. Okay, so there are other indices we will study that solve this problem. So conventional indices are not anymore there, but the BRIN is the closest thing to a conventional indices that we have nowadays. So it's a proper, actually, time to talk about it because this is really, a twist on conventional indices, if you like. Now, this is called a block range index. So I want you to remember that it is really very useful when it comes to working with ranges. Okay? Generally, a BRIN index is nothing but a sparse index, but a different sparse index than what we have seen before. But it's a type of a sparse index. Okay? What's unique about it, what's different about it, is that even though it's a sparse index, we're not going to maintain a single value, we're going to maintain ranges of values. Okay? Which range are we referring to? We're going to store the smallest value and the largest value that appears in every page in the index. So if I have like 100 pages, I need to go to every page and find out the minimum and the maximum, and that's what I'm going to store in the index, the minimum and the maximum, as one entry. Okay, so minimum, comma, maximum, and then a reference to that page. Okay? Now, if you're building a BRIN index on the column used in sorting the table, that's the best scenario. Why? Because the values in that column are already sorted because you're using it to sort the table, the rows. So the values are already sorted. So that means when you go and create a BRIN index, the creation process will involve the following. You will load every page that belongs to this table and grab the minimum and maximum value in that specific column, and then that's it. Okay? So constructing a BRIN index on the column used to sort the table is super fast. Here is an example of a BRIN index. What you see on the right are the table's pages. So I got only 4 pages I'm showing you here. And what I'm going to do in the BRIN index, I'm going to scan this column I'm building the index on and keep this minimum and the maximum values with me. And I can easily do that by looking at the first row and looking at the last row of every page. And then I put a reference to that page. So now I know that, if I'm looking for a value between 10 and 20, then I gotta follow the reference to that page, that first page in the table. If I'm looking for the value 55, I'm going to, say 45 for now. I'm going to follow the entry that says 40, 50, and I will go to the third page in the table. Okay? So the ranges are actually helping me a lot. Well, if I have lots and lots of pages, okay, perhaps I have 500,000 pages in this table. That means I will have the first level in the BRIN index will have 500,000 rows, because for every page I'm maintaining the minimum and maximum, and if I have 500,000 pages, then I have 500,000 rows. That's ugly, and there is a good chance this is not going to fit in memory. So we could actually, or even if it fits in memory because we're going to page it, that's still a lot of rows to process. So what we can do is we could create a multi-level BRIN index. So 10 and 38 are the range of values that's bounded between the two rows in the leftmost block drawn here in the screen. As you see, 10, 20, 30, 38. So I'm saying that those two pages, the ranges of in there is between 10 and 38. The smallest in the first one and the largest in the last one. Now, same thing for 40 and 70. Now when I get a query, so let's start from with value equal to 60. I will skip 10,38 and I will follow 40,70. And then I will again check the index, the first level BRIN index for, where is the 60 until I find it, if that's what I'm looking for. Okay? And that takes me, I will go to 60, 70, and that takes me, I follow the reference and I will go to this last page in the table that shows up at the bottom right of the screen. Okay? So, BRIN indices are interesting because with these ranges, I can know immediately if I'm interested in this page or not. Okay? So let's say, for example, I'm looking for 55. I don't even need to load the table to know that 55 does not exist. I can know that from the BRIN index. I will follow first 40 to 70 to where it says 40 and 50. And then I will realize I'm looking for 55, so I will move on to the next one, and the next one starts from 60. Since there is no 55, then it doesn't exist in this table. So, one rule we're going to set with every type of index we discuss, we're going to talk about when should we use this index. Because we are going to cover actually many indices. And every one of them is used, or it's best used in a very specific scenario. Okay? So this is the first one we're covering this semester, the BRIN index. And the question is when to use this BRIN index. Okay? I'm going to start with the second bullet in this slide. Let me read it. It says, if you're doing lots of searches for data which belongs to a small range in a huge table that has a much wider range stored. What's the story here? The story is, I have a range of values. Let's say it goes from 1 to 1 million. But I am running lots of queries that picks a very small, narrow range within this big range. So the range goes from 1 to 1 million. But most of the time I'm running queries that will return to me only, say, 100 or 200 rows, consecutive rows. So out of the million, I'm getting back 200 consecutive rows. Okay? So let's say, for example, you're storing, another example, if you're storing ages. So age will vary from 0 all the way till, say, 130, and that's probably like the longest someone would live. Now, if you look at your queries that you're finding to this database, and you find that wherever you're querying by age, you're only querying between 50 and 60, and you're ignoring the rest. You rarely query 100 or 90 or 80 or between or greater than 80. Okay, you're always querying, say, between 50 and 60. For some reason, for some weird reason, maybe this database belongs to an insurance company, and they're always interested in finding out what people are doing when they're between 50 and 60, okay, or how frequent people die between 50 and 60, whatever, okay? But you're finding always between 50 and 60, and the range spans from 0 to 130. We call this type of query low selectivity query because it will always return to you a small subset from the total number of rows that it could ever return, okay? Now, for low selectivity queries, for this scenario, BRIN indices are great. Why? Because using the ranges, you can narrow down quickly, super quickly, Actually, it's extremely fast compared to any other index we're going to study. You can narrow down where are you going to look in the table to retrieve the rows that belongs to your result set. Okay? So this is exactly when you should start thinking about using a BRIN index. For all other scenarios, don't use it. Okay? And we will see many other scenarios later on. Now, Also, let's go back to the first point. Also, what you could do as a second option for you to use a BRIN index, or a second reason why you would think why would you use a BRIN index, if you are actually running aggregate functions on values where you're not necessarily counting the number of values that appear, but you are trying to find out some statistical information about the values that shows up. Okay, for example, if you would like to figure out whether a specific number, say the number 50, appears approximately half the time in the table, or if you would like to sum up the values that appears within a certain range. So again, we go back to this range or low selectivity issue. Okay, or you'd like to find out the smallest value in the table, or the largest value in the table. So there are aggregate functions that you could at least partially answer by looking at the index data, since you have these ranges. Okay, but not all aggregate functions, so you have to consider each one separately to decide. Okay. Now, means, for example, mean calculations are all very interesting because there are approximate mean calculations that will enable you to calculate an approximate mean, not the exact mean, but an approximate mean using the BRIN values, the ranges that appears in the BRIN. And instead of going to the table, touching the column, perhaps you have like 100 million rows to figure out the average, the mean. Well, if you can get an approximation of that using the BRIN, that's fine. And there are actually techniques you could do to actually do that. So you can grab the values in the BRIN, all the values in the BRIN, and just sum up their values and divide by their count, and you will get an approximate mean, which is better than nothing. Not exactly an accurate mean, but it's an approximate mean. Now let me show you how you actually create a BRIN. So every database engine you will come across will have many indices. That's why we discussed them in the course. Okay, we're talking here many as in tens of indices. As you will see later on with Postgres, there is a whole page that is dedicated to what Postgres supports. And they support something like 20 indices. Okay, if we count all the variations and the plugins. Now, for every database engine, because the standard for writing SQL does not specify how the programmer is going, or the database administrator is going to specify which index to be used. Every database engine will do it in its own way or in its own flavor, okay, in terms of the syntax. So in Postgres, if you would like to use BRIN, what you're going to do is you're going to use the create index statement, just like we have seen before, giving it a name on some specific table, on some specific column, and you say using BRIN. And this will happen or will repeat for all indices we look at. So later on we will say using B3 or using hash and so on. Okay? So this is how we create a BRIN index in Postgres. And I have linked for you here the documentation that you should read regarding the BRIN index implementation in Postgres. The takeaway is a BRIN index stores the minimum and maximum values in each table page. It is efficient only in two scenarios: analytical queries and queries involving narrow range search on a column with a huge range of values.